3 PLC timer instructions catch every beginner exactly once. Ton, TOF, TP. They look almost identical on the rung. They do completely different jobs. Mix them up and the rung looks correct, but the machine behaves strangely. This video walks the whole family. The shared structure, the behavior of each one, the real rung each timer belongs in, and the one mistake almost every beginner makes the first time. Every modern PLC timer follows the same shape. The IEC 61131-3 standard defines it. There are 4 pins. The IN pin starts and stops the timer. The PT pin sets the preset time in seconds or milliseconds. The Q pin is the timer output, a Boolean bit that other rungs read. And the ET pin is the elapsed time so far. ET is a value, not a bit, so other rungs can read how much time has passed. The 3 different timer instructions all use these same 4 pins. The only difference between them is how IN, Q, and ET interact during execution. Learn the shape once, and you can read every timer rung in any vendor environment without relearning. The first timer is TON, or timer on delay. It is the most common timer on a factory floor. When IN goes true, ET starts counting up from 0. When ET reaches PT, the Q output turns true. While ET is below PT, Q stays false. When IN drops to false at any point, both ET and Q reset to 0 immediately. TON answers the question, wait this long after the input goes true, then turn the output on. The most common use is a motor start delay. The operator presses start, but the actual motor coil energizes 3 seconds later, giving the operator time to clear the area. The other classic use is debouncing. A noisy push button is wired into IN with the preset at 50 milliseconds. Q only goes true if the button stays pressed for the full 50. Brief bounces never make it past Q. The second timer is TOF, or timer off delay. It works the opposite way. When IN goes true, Q immediately goes true with no delay. ET stays at 0 while IN is true. When IN drops to false, ET starts counting up. While ET is below PT, Q stays true. When ET reaches PT, Q finally goes false. The pattern is, keep the output on for a while after the input drops. The classic use is the cooling fan run-on. The machine stops, but the cooling fan keeps running for 30 seconds afterwards. The motor cools down before the fan drops. Another common use is the conveyor stop delay. A part sensor triggers a stop request. The conveyor keeps running for 1 second, so the part fully clears the photo eye before the belt halts. The third timer is TP, the timer pulse. It works very differently. When IN sees a rising edge, a clean transition from false to true, TP holds Q true for exactly PT seconds. After that, Q goes false. Whether IN stays true or drops to false during that window does not matter. The pulse is committed at the rising edge. Another rising edge will not retrigger the timer while it is running. TP answers the question, fire a fixed duration output every time the input is triggered. The classic uses are everywhere. A solenoid valve that should open for exactly 2 seconds. A strobe light that flashes for half a second. A warning horn that sounds for 3 seconds before a robot arm moves. Anything where the duration is fixed and the input duration is irrelevant. Here is the single most common beginner trap. The intended behavior is a fixed duration pulse. Open a solenoid valve for 2 seconds. The beginner reaches for TON, sets the preset to 2 seconds, and wires the start button to IN. The rung looks correct, but the behavior is wrong. If the operator holds the button down, Q stays false for 2 seconds. Then Q goes true and stays true until the button is released. If the operator releases the button early, the timer resets and nothing happens. The valve never opens for exactly 2 seconds. The right instruction is TP. A rising edge on IN, regardless of how long the button is held, fires Q true for exactly 2 seconds. That is the fixed duration pulse the rung actually needs. There are vendor differences to be aware of when moving between environments. The IEC standard defines the timer outputs as Q and ET. Allen Bradley RS Logic's 500 and older Studio 5000 use TON.DN as the done bit instead of Q. TON.ACC replaces ET as the accumulated value. The names are different. The behavior is identical. Mitsubishi GX Works historically used a coil-style timer, where the timer's coil acts as the IN pin and a separate contact reads the output. The mental model is the same. Just look up which symbol or pin on which vendor maps to the IEC concept. The mistake to avoid is assuming a different vendor invented different timer behavior. They did not. The standard is shared. The pin names and graphics are not. Run all 3 rungs yourself at plcsimulationsoftware.com. The lessons on the free tier cover TON, TOF, and TP step by step, with the timer behavior visualized live as the rung executes. You can watch ET tick up. Watch Q flip at the moment ET hits PT. Press ion on and off, and see exactly how each timer family responds. Next video covers PLC counters. CTU, CTD, and CTUD. The same structural pattern as timers, but counting events instead of seconds. Subscribe. There is a new video every Tuesday. See you in the next one.